we're going to do some fantastic work with negative radicals. So when we look at what we had done previously, we saw that any two numbers that we multiplied up to this point, such as the square root of 2 times the square root of 3, we would just multiply those together and we would get the square root of 6. Now because these are negative, less than 0, we can't apply that same property. We've got to do something a little bit different. Now earlier you had seen that the square root of negative 1 equals this imaginary number I, which is great in electricity. So when we look at this, we need to rewrite each of these radicals as a product of two components, two factors, but we got to include this negative 1, this square root of negative 1. So if we write this as the square root of negative 1 times the square root of 3 times the square root of negative 1 times the square root of 7, notice we've applied this ability that we have of breaking a single radical into a product of two radicals. And now if we apply this property, we have this I, which is the square root of 1. We still have the square root of 3. We have the second I here. And we have the square root of 7. Now because of the commutative property of multiplication, we can order these any which way we want. So I'm going to rewrite the i's first. The i's have it. They're in charge. And now, I squared, which is I times I, and again we can break this product, we can make it into the square root of 21. And just like this property, there's a second property. If we square this side and square this side, I squared equals negative 1. So if we substitute that into our simplification, we have the square root of negative 3 times the square root of negative 7 equals negative 1 square root 21. So now we're going to do a second example. So notice here, you also might simply say negative square root of 21 versus the negative 1. Both are equivalent, but whatever you choose, both are good. Now when we look at this example, it follows the same format as the previous example we just did. So I'm going to rewrite this using the negative 1 as factors of both negative 12 and negative 6. Now I'm going to rewrite these negative 1's as i's, and I'm going to move them forward as I did in the previous example. And I'm going to get these last two, square root of 12 and square root of 6. Now again I'm going to simplify. I times I is I squared. 12 times 6 is 72. Now we have negative 1, or negative, square root 72 as our radical. Now, unlike 21, it doesn't have, 21 does not have a perfect square, remember this list, as a factor. So that's how we know that's done. 4 doesn't go into 21, 9 doesn't go into 21, and so on evenly. But we know that 4 goes into this. If we divided it, that would go into here. 9 also goes into this. 36 also goes into this. And you can check this by simply typing 72 and divide by 4. 72 divided by 9. 72 divided by 36. 16 and 25 don't work as factors that get us to integers. And again, we want the largest of them. We can begin with 4 and we can begin with 9, but we'll have to do a couple extra steps in between. And I recommend that you try to do that or ask for help in learning that. So if I take 36, which divides nicely into 72, and we get the factors of the square root of 32 and the square root of 36 and the square root of 2, we know that the square root we always want to write first because we're going to multiply that by our coefficient of negative 1, and we'll have negative 1 times 6, which is negative 6, times the square root of 2. And there's the simplification, using the negative numbers, recognizing that when we got to this point, that we needed to look for a perfect square as a factor so we can go a little bit further and simplify it completely. Right? Go to it.